why some people complain about quantum mechanics and they say it is incomplete or inconsistent, and how this is coupled with the notion of time. Would time have an algorithm of its own? Let's find out in this episode. Imagine a comet colliding with Earth and wiping out all civilization, every life on Earth, and then we get an empty planet. No single living creature or living thing lives in anymore. What happened to time? So time would still continue. I mean, the universe is still moving, everything is happening. So our notion or our perspective just has disappeared from Earth. And here we come to the notion of time. So we use time on a regular basis. Every day we ask about time, when we are gonna meet and what we are gonna do in the evening. So the notion of time is sort of built in our lives, our lifetimes, and lifetime of a particle. Everything has a moment in time to start and to end. And this is how Isaac Newton has envisioned time. So time is sort of like a river that flows everywhere. So it's a fixed river, and this river gives us an external parameter so we can measure the changes that happen in physical quantities with respect to this external parameter time. So the change in distance with respect to time would give us the speed, and the speed with respect to time would give us the acceleration. And then we can have the force, and we can have the momentum, we can have the electric current, and so on. So time is sort of an external thing that we can use to measure the changes and quantify them. If you throw a ball in the air and this ball will follow a projectile motion, then you can know precisely the position of this ball in each moment of time just by solving Newtonian equations. So that river gives us this ability. When we go to relativity, this river is not absolute anymore. This river becomes relative to the reference frame or the current observer. So for example, if we are now on Earth, the time would tick differently on Earth than some spaceship next to a black hole, for example, or a rocket that's traveling by a half speed of light. Then the time would tick differently. So of course, when we are on Earth, we don't feel this. We don't feel this relativistic nature of time because we are on the same planet. So time sort of is still, this river flows with constant nature with respect to us, so we don't feel it at all. However, we only see these differences when we compare this flow of time, in Earth with respect to the flow of time with someone living in a rocket that travels at the half speed of light. So we will see that the time is ticking there slower than it ticks here on Earth. The same when we go to general relativity, then the distinguish between gravity and the acceleration or the frame of reference that accelerates with the same acceleration is not distinguished anymore. So this is the equivalence principle, and by that, as a result of this, the space-time or the time is intertwined inside this fabric of space, and then we have the space-time, and then basically time would tick differently with respect to the curvature of the space-time. So the time here on Earth will be much faster than someone living in the vicinity of a black hole, because the time there will tick much slower, and this is known as gravitational time dilation. So far so good. We have the time, we can use it to measure the changes. Still, we are on Earth, we can use it. However, the notion of time or the time itself, the ticking of time, will differ from one frame or with respect to one observer than another because of the relativistic nature of time. These rivers or different rivers of time would flow differently depending on the reference frame speed with respect to another frame. The take-home message here is that if you are in Newtonian limit or you are in a relativistic limit, still time, you can use it as an external parameter to measure the changes in the physical quantities that you are using in your particular frame. So we can determine the speed of a train when we measure the change in distance with respect to time. This time in Earth, the ticking of this time or the flow of the river of time would be different from the flow of time with respect to an external observer that moves by the half speed of light. However, when we are in the frame of that space rocket, then the time there we can use it also as an external parameter to measure the changes in the physical quantities there. However, the changes there and here would differ. And this is also can be manifested by the twin paradox. So if I have a twin of mine and I keep living on Earth for 10 years, and my twin would travel with a space rocket with a half speed of light for a few years, then when he comes back, and then I will grow much older, even I might not exist when he comes back. So this is the relativity of time. So we still measure the changes. However, we can compare these changes, and that gives us the notion of time. So time would dilate with respect to different observers. When it comes to quantum mechanics, time would give us a very different and strange notion. And this is what gives rise to the problems of what people claim to be inconsistency or some contradictions in quantum mechanics. And to understand this, let's borrow some examples from quantum information theory. You can use the notion of a qubit. So the qubit is the unit of quantum information. And now we have the quantum computers. This also can test some limits of quantum mechanics. So let's imagine this qubit now is sort of standing still in the ground state. So it will be in the zero state. It is similar to a classical bit. It will stay in this state for quite some time if left undisturbed. So what happened is that this qubit has the ability to jump into what we call a superposition state. So it acts or it behaves when it's in the zero state as a classical bit. However, it has an ability that when you apply specific operation on it, it can jump to the superposition state. So if you have the qubit in the zero state, then this is sort of your state. You can describe your state function as zero. But then you can apply the Hadamard gate. And the Hadamard gate is sort of a quantum operation that will project or transform the state of the qubit from being purely in zero to be in a superposition between the 0 and 1. So it will be partly in 0 and partly in 1. And this superposition would mean that we have two situations that coexist together. It is different from the classical superposition. In quantum mechanics, the superposition is that we have different situations that coexist together. This different situation means that you have many configurations that coexist. However, in classical mechanics, it's different because you are sort of, if you have two waves, water waves, making a superposition with one another, you get sort of the total sum of the two waves. So you get the total interference. And this could be constructive interference or destructive interference. So in the constructive interference, they are reinforcing one another. And in the destructive interference, either they are destroying one another totally or partially, and so on. So you can see the total state, or you can see the total amplitude from this superposition. And this is different from the quantum mechanics because we have in quantum mechanics the coexistence of multi-configurations or multi-situations. So we have the situation where the qubit is in the state 0, and we have another situation where the qubit is in state 1. And these two situations coexist together. So we say that the qubit is partly in 0, partly in 1. Here is the thing. Now we used one quantum operation to transform the qubit from being sort of in a semi-classical state, still in a quantum state, but it has a definitive state or a situation. And then we projected it into a superposition. So it's now sort of, it has a quantum state, and that quantum state, the qubit can exist in a superposition or partly in 0, partly in 1. And then when we perform a measurement, we only end up with one of these two values. And since we have the coefficient of 1 over root square of 2, then the probability of finding the qubit state in the 0 state or in the 1 state is correlated or proportional to this probability, is related to the square of this number. So now the probability is half. So if we perform this measurement 100 times, when we prepare these qubits in superposition 100 times, we should typically get, in theory, 50% the qubit will be in the 0 state, and the other 50% the qubit will be in the 1 state. So far, so good. However, here is the thing. Here is the problem comes in. We have the qubit in the state 0, so it was untouched, and then we applied an operation that can create the superposition. So now the superposition is created. We have now created a bubble in the classical world of the classical universe. This bubble contains the quantum properties. One of them is the superposition of this qubit. If we leave the qubit without touching it, it will live for some time, and then this superposition will decay. So we have what we call it dephasing time, where the relative information between the state 0 and 1 will disappear. Or we have another time also called the decoherence time, and this is a time where the qubit state will relax and then will return to the default state, which is the 0 or the ground state. So after some time, this quantum world or the quantum bubble that we have created will collapse, and then it will end up returning to the original state. Okay, so far so good. So where is the inconsistency here? The inconsistency comes in the following. So you have the qubit in the ground state, you have created this world, and then when you do the measurement only will retrieve for you one outcome, one state only, either the 0 or the 1. So in a nutshell, if we describe the qubit with a state function or a wave function, we call it the collapse of the wave function. So it means that the wave function that describes this probability nature or this multi-configuration or the multi-state situation of the qubit would collapse. And this collapse will result in only one state when we perform the measurement. If we don't perform the measurement, the wave function will collapse and it will end up also in the 0 state. When we measure, it either could be 0 or 1. So here is the thing. Schrödinger equation can describe perfectly the evolution, either in time or the time evolution, or for example, time independent nature of the wave function or the state function. So it can describe how this state function will evolve in time, backward and forward, because time is reversal in quantum mechanics. So you can apply unitary operations. In this operation, it's called unitary because also you preserve the norm of the wave function. So you can propagate this wave in time, backward and forward. However, when you do the measurement, this measurement is not described by Schrödinger equation. So you end up having like sort of abrupt change. You enforce the collapse of the wave function by letting the system interacts with an observable. This observable, you can know the eigenvalues of it, like the z-axis of a magnetic field or anything. So you can detect either if you have, for example, an electron with a spin half, so either you will end up with a spin up or a spin down. So this interaction would force the collapse of the wave function, and then the inconsistency comes from this. Why Schrödinger equation cannot describe what happens prior to the creation of the state function, and why Schrödinger equation cannot describe perfectly what happens at the measurement and after the measurement. So time here behaves differently. So the time is reversal in this quantum bubble that we have created. When we created the system until we measure, the time is reversible. However, once we perform the measurement, time is not reversible anymore and is only moving forward. So now the sort of the measurement forced the quantum system to return back to the classical system. So many people complained about this. We have Roger Penrose who complained about this and said, okay, there is logical fallacy here. Many physicists and theorists already in the past have already pointed out to this, like Wegener, but also Einstein and Schrödinger himself. What happens to this? Why the wave equations or the wave quantum equations cannot describe the propagation or the evolution of the wave nature of the quantum system during the measurement and after the measurement? What happens in particular during the measurement? So you have these probabilities, you have all of these states, but only one will be fixed. So in my opinion, I don't see a contradiction or something wrong here. Maybe we need more information, maybe we need more knowledge about what happens in the system at this fundamental level. So when you do a measurement, you make an external object or an external field interacts with your quantum system. So the result of this interaction is that you will end up measuring an eigenvalue of your observable. And that eigenvalue would be correlated to one of the states that was involved in the wave function. So we call it the collapse of the wave function. So the wave function has collapsed. So this collapse have already happened, and then the other possibilities have disappeared. So there were many interpretations and many notions of this, like we have the Copenhagen interpretation, but also the many world interpretations and so on. But the idea is that why this should indicate inconsistency in quantum mechanics, rather than it indicates that maybe we are lacking some knowledge about what happens during the measurement and after. So there was some paper in literature have already tried to describe the interactions of apparatus. So when you approach a quantum system with apparatus, this interaction will already influence the state function, will influence it gradually, and during this influence, you will favor one of the results more than the other. But this is normal because you have asymmetric devices, so these devices will interact with the quantum system and will make sort of or induce some bias in the system. So that's okay. The second thing is that theoretically we can know what happens because we have the density matrix, and we can clearly state the possible coexisted situations of the wave function, all the states, with some weights. So these we can describe immediately. We can have a peak at this, and then we can have our projectors. But the wave equation itself sort of stops at the measurement. And I don't see this weird or anything, because now after the measurement, your system has been turned into sort of, you forced the classical world or the classical nature. So maybe we lack some information here, but this wouldn't induce inconsistency. Some people also indicate that, okay, now we have entanglement, and if you have two qubits, like the QA and the QB, and then you perform the entanglement operations, like the Hadamard gate first on the first qubit, and then you have the CNOT gate, where the first qubit is the control and the second qubit is the target. The result of this, you will end up having two situations, 0, 0, and 1, 1, and those are weighted by 1 over root square of 2. Then, if you measure one of the qubits, let's assume it is the first qubit, then if you find it in the 0 state, the only situation where the two qubits, the only situation in which the first qubit is in the 0 state is the kit 0, 0. It means that when you perform this partial measurement and you communicate your finding to your colleague, like Alice, for example, Alice will expect or should expect her qubit to be in 0 because of this is the result of the entanglement. So some people will try to draw some logical or non-logical bias here, but then again, these rules of quantum mechanics would prevail. So some of this interpretation would assume that, okay, you have many worlds, and this many worlds would mean that in each universe you have 100% probability to find one particular state, depending on the world you are in. However, this also has some problems in it. So if you have the coherence time, then the coherence time would describe the lifetime of the qubit. So if you create a qubit in a superposition, you have some time. This time in which is that how much is a quantum superposition is surviving. So we have the decoherence and we have the dephasing time, which I pointed out. Once the quantum state decoheres, it will return back to the default state, which is the ground state. In our case, it is the 0 state. So without measurement or anything, after some time, the quantum state will return typically, or in most of the architectures, will return to the ground state. However, when we do the measurement, we do it during the coherence time, not after. So when we do it during the coherence time, we can measure the qubit to be either 0 or 1. So let's assume if we found the qubit in one state, does it live forever in the one state? No. So we only get the eigenvalue, or we get the state 1, but then after sometimes the qubit will relax to the ground state, because this one is sort of like an excited state. So this quantum system will not stay very long in it, and it will relax again to the ground state. So this is why people complain about it. And this is how the time contributes to this, that the time is reversible in the quantum world, but then after the measurement, and it sort of has one unified direction and it follows the classical world laws of physics. This also can be extrapolated to the problem of the unified field theory. So how we can combine quantum mechanics and general relativity. And if we do this, we'll end up having discrete spacetime. So we'll find, or we are gonna see the grainousness concept of the universe, that the universe is sort of now becoming grainized. So it's sort of a combination of very, very tiny small grains, or we will get pixelation of the space-time fabric. So when we look to the space-time, it is not a continuous fabric anymore. It is now pixelated. So we are gonna see in pixels. So the space will be quantized, will not continuous anymore, and the time will be quantized. And this is actually very problematic, and this gives a rise for quantum gravity, because if you have the space is quantized, it means that the meter, which is a portion of a space that we know, is no longer continuous, and it is quantized. Of course, this is very, very tiny distance that's related to the Planck's length, and of course the time is the same. It's also will be related to Planck's time, but then it would mean that if you have very small operations that happens, then you have a glitches in space. You cannot have this in between the moment. You have to jump from this little moment to the other moment and leave the gap in between. So this is also will contradict some things about the continuity of the space-time and will give us a new notion about the metric of space-time. So far, quantum gravity is still a theory. However, this also comes as a birth from quantum mechanics. Now I have outlined what are the concepts or why some people complain about quantum mechanics, and this is not an actual or should not be an actual complaint. It might be incompleteness in knowledge, but the quantum mechanics is pretty much a very solid theory. So its only knowledge is that what happens at this abrupt change when we interact with an external object, that external object which we use in the measurement is what forces the quantum system or what forces the collapse of the wave function. So some scientists say, okay, this is a conscience of the observer, but then we can observe without having a human being. So this is a case. So if we imagine some universal comet or a very huge planet that came and collided with Earth and then wiped out all the civilizations and every living creature on Earth, we are gonna end up with an empty Earth. Time is still ticking. Time is still outside ticking. And then when still the quantum properties are happening, some particles are localized, the probability of or the wave function nature will be there. It will not be impacted by us. So the conscience here is not that strong to impact the way we measure. It's now we impact the measurement by just enforcing this interaction. So if you have more questions about this or you have different interpretation to this, feel free to drop it out in the comment. In next videos, we are gonna also discuss the complex nature of the wave function and how it could be a two-dimensional objects, and then combining the real and the imaginary part would give rise to the nature of the wave function. Now let's ask ourselves, would time then have an algorithm? The answer is no, because now the algorithm of time won't happen. You can have a time as an external parameters. These external parameters can change based on the relativistic view of your reference frame or your observer, but still time a parameter outside. So you cannot use it as an algorithm or anything. You can just use it in a way that you can define or measure the steps of your algorithm. And also if you have a different interpretation, just drop it in the chat. Until then, see you.